We've talked about four different families of symmetric functions. Now let's start to look at how they're related to each other, starting with the elementary symmetric functions and the monomial symmetric functions. First of all, recall that if k is an integer, then the kth elementary symmetric function is defined to be a sum over indices I1 less than I2, etc., up to ik of the product xi1 through xik. So this is a sum of all monomials of k distinct variables. Then we can define, if we have a partition lambda, which is, let's say, lambda 1 through lambda L, E lambda is the product of E lambda 1, E lambda 2 up to E lambda L. But if lambda is a partition of n, then E lambda belongs to the homogeneous degree n symmetric functions. That's because ek has degree k, and then if we add up all the parts of lambda, if they add up to n, then we've got something that's homogeneous of degree n. And we know that the monomial symmetric functions form a basis of lambda n. So a natural question is, how does E lambda expand in the monomial basis? Well, let's do an example to see, at least in one case. E3 is easy, because that's a sum of all products of three variables at a time. Which is exactly what M111 is. All of these exponent sequences are 1, 1, 1. Now E21 is a product of E2 times E1. So it's x1, x2 plus x1, x3 plus x2, x3, etc. times x1 plus x2 plus x3, etc. And if we look at the monomials that come out of multiplying this out, we see x1 cubed is not going to be there, because we would need an x1 here and an x1 squared there, and there is no x1 squared here. So that one comes out not at all. x1 squared x2 comes up, well, we can't have an x squared x1 squared here, so we need an x1 in the left factor and the right factor, and then we need an x2. So I guess it's going to come up once, x1, x2 times x1. And then x1, x2, x3 is going to come up when we have x1, x2 here and an x3 there, or x1, x3 here and x2 there, or x2, x3 here and x1 there. That one's going to come up 3 times. Now, since this is definitely symmetric, it's okay that we just looked at the monomials x1 squared x2 and x1, x2, x3. That is, the coefficient of x1 squared x2 equals the coefficient of x1, x2 squared, which is the coefficient of x1 squared x3. So basically, the coefficient of x1 squared x2 equals the coefficient of m21. Similarly, the coefficient of x1, x2, x3 is equal to the coefficient of x1, x2, x4, etc. So also the coefficient of x1, x2, x3 equals the coefficient of m111. So that means that E21 equals 0m3 plus 1m21 plus 3m111. And if we look at the last one, E111, so that's x1 plus x2 plus x3, etc., times x1 plus x2 plus x3, etc., plus times x1 plus x2 plus x3. The coefficient of m3 equals the coefficient of x1 cubed, which is, there's one way to get x1 cubed. We take x1, x1, and x1. The coefficient of m21 equals the coefficient of x1 squared x2, which is, so we could take x1, x1, x2, or x1, x1, x2, or these two x1s and that x2. That's going to be 3. And the coefficient of m111 equals the coefficient of x1, x2, x3. And there's 6 ways we can do that. Take 1, 2, or 3 here, something we haven't taken there, and the last thing we haven't taken there. So there's 6. Now this method of looking at the coefficients of certain monomials to get the coefficient of the monomial symmetric function always works. But there is a formula that's a little bit quicker to use. In particular, E lambda is the sum of, let's say, capital M lambda mu, little m mu, where m, capital M lambda mu, equals the number of let me say column strict Young tableau. Of shape lambda transpose and content mu. So column strict means increasing in columns. And content mu means mu1 ones, mu2 twos, etc. So let's do an example of that. So we'll do the same example. We should get the same numbers. So if we expand the third elementary symmetric function in the monomial basis, we get that it equals something m3 plus something m21 plus something m111. So by this rule, we should draw a Young diagram of shape lambda transpose, so that's 111. And then we should try and fill it with 3 1s, or 2 1s and a 2, or a 1, a 2, and a 3, in such a way that it's column strict. So to fill it with 3 1s, well, that's not column strict, because we're only weakly increasing in the column. So there's no way to put 3 1s in this tableau and have it be increasing in the column. 2 1. So here's a Young 2 1 transpose is 2 1. So we want to put, oh, I'm sorry, we're still doing, the shape is given by this number. We want to put 2 1s and a 2 in there. Well, the best we could do with this, but that's not column strict either. So there aren't any. Now if we have a single 1, a single 2, and a single 3, there is a way to put those into this Young diagram to make a column strict tableau. We put the 1 down there, and then the 2, and then the 3. There's exactly one way to place them in there. So E3 equals M111. We knew that. Now let's look at the expansion of E21. So E21 equals something M3 plus something M21 plus something M111. 2 1 transpose is 2 1. So we want to put 3 1s in there so that we have a column strict tableau. Well, we can't do that. 3 1s makes it not column strict. But if we try and put 2 1s and a 2 in there, we will succeed. If we put the 1s down here and then the 2 up there, this is column strict. That's the only way to do it because we don't want to put the 2 1s in the same column. And then if we have a 1 and a 2 and a 3, then there are several ways to fill the tableau and keep it column strict. We could put 1 and 2 in the first column. We could put 1 and 3 in the first column. And we could even put 2 and 3 in the first column. The only rule we have is that in a column, the numbers have to increase. So there's 3 ways to do that. And that tells us that E21 equals M21 plus 3M111. And finally, if we write out E111 in terms of the binomial symmetric functions, then we get, let's see, so the shape is 111 transpose, which is 3. We want to put 3 1s in there. Well, there's only one way to put 3 1s in there, and it works this time. On the other hand, we could put 2 1s and a 2 in there we could put 1 1 2 or 1 2 1 or 2 1 1. So there's 3 ways to do that. And then if we put a 1, a 2, and a 3 in there, obviously there's 6 ways. We're just looking at the permutations of 1, 2, 3. So that means that, I'll write it up here, E111 equals M3 plus 3M21 plus 6M111. Alright, so this rule is E lambda equals the sum over all mu partitioning n, capital M lambda mu, little m mu. So this coefficient is the number of column strict Young tableau of shape lambda transpose and content mu. Now let's look and see why this is true. Why do we get the same answers using the tableau that we did when we multiplied out the variables? So this is my claim. We have E lambda equals E lambda 1, E lambda 2, E lambda 3, etc. Say E lambda L. A typical monomial in x1 through, let's say, xn, when we multiply this out, is something like xi1 through xi lambda 1. That'll come from E lambda 1. And these indices are going to be increasing. And then something like xj1 through xj lambda 2. These indices are going to be increasing, and that comes from E lambda 2. And then x, let's say k1 through xk lambda 3. Etc. Now we can write these increasing index sequences in a tableau, and we'll get I1 through I lambda 1 in the first column, J1 through J lambda 2 in the second column, and K1 through K lambda 3 in the third column, etc. And so we have a column strict Young tableau of shape lambda transposed. Now the number of times we get a monomial of the form x to the mu1, let's see, x1 to the mu1, x2 to the mu2, x3 to the mu3, and the expansion is the number of such tableau containing mu1 ones, because every 1 here stands for an x1, mu2 twos, because every 2 stands for an x2, etc. So that's exactly what the formula is saying. M lambda mu is the number of column strict Young tableau of shape lambda transpose and content mu. Mu1 ones, mu2 twos, etc. Now we can actually improve on this formula a little bit. Let's look at the numbers we got for the case n equals 3. We said E3 equals, if we write out the 3 equations, we write this as a vector. The coefficients we got were 1, 0, 0, 3, 1, 0, 6, 3, 1. At least if I write the monomials in the order. I guess this is backwards from what I did before. Anyway, so if we write the order appropriately, we can see that there's a lot of zeros in the matrix and there's some ones on the diagonal. If that always happens, then that means that the elementary symmetric functions are a basis also of the same space that the monomial symmetric functions are a basis of, because this matrix is invertible. Not only are they a basis of the same space if the coefficients are real, but they're a basis of the same z module if the coefficients are integers, because an upper triangular or lower triangular matrix with ones on the diagonal has determinant 1, and therefore it's invertible over the integers. So to refine the claim a little bit, we can say E lambda equals M lambda transpose plus a sum over all partitions mu which are less than or equal to lambda transpose, less than, because I already put the equal case over there, capital M lambda mu, little m mu. So we're always going to have 1 on the diagonal, and then all the non-zero numbers are going to fall below the diagonal, at least if we write the bases in this order. So this is saying that M lambda transpose equals 1, and M lambda mu equals 0 if mu is not less than or equal to lambda transpose. So capital M lambda transpose equals to 1 is easy. So if we try and put lambda transpose 1 ones, lambda transpose 2 twos, etc. into a tableau, a Young tableau, actually to a column strict tableau, a column strict Young tableau. Of shape lambda transpose, then there's only one way to do it. We need to put the lambda transpose 1 ones in the first row, the lambda 2 transpose 2s in the second row, etc. So we'll get, if this is lambda transpose, then there's lambda transpose 1 ones, and then lambda transpose 2 twos, etc. Lambda transpose 3 threes, so if we want this to be strictly increasing, that's the only thing we can do. And then we're saying M lambda mu equals 0 if mu is not less than or equal to lambda transpose in the majorization order. So now let's suppose mu is not less than or equal to lambda transpose in majorization. Then that means for some index j, we have that the first j components of mu add up to something greater than the first j components of lambda transpose. but each one of these is the number of boxes in a Young tableau. Number of boxes in the jth row. Of a Young tableau of shape lambda transpose. Now if we've got more 1s through j's, mu1 through plus the sum of mu1 through mu j being greater than this means there are more 1s, 2s, etc. up to j's than we can fit in, this is how much we can fit in the first j rows. So if there's more 1s, 2s, 3s, etc. up to j's than we can fit in the first j rows of a tableau, then we're going to spill over into the j plus first row. If we put them in the tableau at all. But then if we put these j numbers into a say the first column, j plus 1 high, then some number has to be repeated. And then that means that the tableau is not column strict. So then a corollary is, as we mentioned before, that the elementary symmetric functions E lambda, as lambda varies over all partitions of n, is a basis of the Z module lambda n. And the reason is that monomial symmetric functions are a basis. And it's related to the set E lambda, lambda partition of n, by a unitriangular transition matrix. Unitriangular is lower triangular with ones on the diagonal, and this is invertible, determinant is 1 over the integers. So therefore that has to be a basis also. The end.